All right, welcome everyone. Today we're going to be looking at polar regions and polar curves. So specifically, we're going to see how to graph polar regions, we'll see how to graph polar curves, and then we'll see how to convert descriptions of these regions and curves back and forth between Cartesian and polar coordinates. All right, so let's start with a few easy examples of polar curves. And in example 1, we're going to graph the polar curve given by r equals 2. R equal to 2 here. So this is a polar equation. And what we're trying to do when we graph a polar curve and when we graph a polar equation is we're trying to find all of the points in the plane that have at least one representation that satisfies this condition. So that's really what we're trying to do. So we want to plot all points in the plane that have at least one polar representation that satisfies this condition. So we want to find all of the points where we can find a polar coordinate representation for that point where the r value is 2. All right, so let's think about one example here. Let's look at this point right here. What's a polar coordinate representation for that point? Well, this is the ray pi over 6. So a way to describe this point is 2 comma pi over 6. So yeah, this point would fall on our polar curve. What's a few other representations for this point? Well, negative 2 comma 7 pi over 6 is another one. This representation doesn't meet this requirement, but that's okay. So we want to plot all the points that have at least one polar representation which satisfies this condition, r equal to 2. So we already found one. So yeah, it's going to turn out that every single point has many different ways we can write it down. Some of them are going to fit the description, some of them might not. But as long as there's at least one representation that does actually fit the description, that point is going to be on our curve. And it turns out that when we're looking at r equal to 2, this is going to be a circle. So r equal to a constant So when r is a constant, this is a circle of radius k. Centered at the origin. So that's why it's helpful to think of the r value as really like a radius, because when r is equal to a constant, it's giving us a circle. So it's going to be the circle centered at the origin with radius 2. And there we go. So this is the graph of r equal to 2. So every single point on here has at least one polar representation where the r coordinate, the r value, is equal to 2. There might be other ones out there where the r value is, say, negative 2. Perfectly fine. So these points are going to have multiple ways we can write them down, but at least one version of this one representation for this point has the necessary condition that the r value is 2. All right, so this is one of our basic polar curves when the r value is a constant. What happens when theta is a constant? So let's look at the graph of the polar curve given by theta equal to pi over 6. So essentially what we want to do here is we want to find all of the points in the plane that have at least one representation where the theta value is pi over 6. So really what we're trying to do, find all points in the plane that have at least one polar representation where theta is equal to pi over 6. This is really what we're trying to do. So let's find our pi over 6 ray. Here it is. And if we look at points on this ray, let's look at that same point. This point right here, we wrote down before that it had coordinates 2 comma pi over 6. So this version of this point, this representation of the point here, satisfies the condition. We wrote down polar coordinates for that point, and the theta value is pi over 6. Now there's other ways to write down to describe this point in polar coordinates. Some of them might not work. So we saw negative 2 comma 7 pi over 6. This version doesn't work, but that's okay. We already found one that does. So we know this point is going to be on our curve. There might be other ones still. 2 comma 13 pi over 6. Again, this is a representation for that exact same point, but the theta value here doesn't fit our description, but that's okay. We found one that actually does meet the condition, that theta value is pi over 6. All right, and it turns out that if we were to graph this, it's a line. So all of the points on this line have a theta value, can be represented as a polar coordinate, or in polar coordinates, where a theta value is pi over 6. So in general, theta equal to a constant k is a line through the origin with slope equal to tangent theta. And we know the slope here is tangent theta because if we have a line that's going through the origin, that means y is equal to mx. Normally a line is y equals mx plus b, but if we're going through the origin, well, the y-intercept is going to be 0. And if we solve this for m, the slope, we get y divided by x. There is a kind of a special case here where we have a vertical line, but we'll disregard that for the time being. But if we divide this by x, we would get the slope, and we know y over x in terms of polar coordinates is tangent theta. So that's how we know the slope of our line here is going to be tangent theta. And so if you know the slope of the line, you can recover the theta value by just using the arctan function. So if you know the slope, you don't know the theta value, well, take your slope, apply the arctan function, and you can use that to help figure out what the theta value is going to be. All right, so let's just talk a little bit more about the points on this line. So there's kind of 3 separate sections for this line here that we want to consider. And they get split up at the origin. So if we look at that origin, what point, or what would the r value be to get that origin value, to get that origin point? Well, that would be r equals 0. Now, what about to get this section on kind of this positive section of the pi over 6 rate, to get this right section here? Well, to get this, we would need the r value to be positive. And then if we look at this section over here, what would we need over here? Well, this is where we would need r to be negative. So for instance, if we picked another point on here, let's say maybe this point over here, how could we write this down in polar coordinates where the theta value is pi over 6? So we want it with pi over 6 as our theta value. And we see that we're 3 units away from the origin, but we're in the opposite direction of the pi over 6 ray. So we're 3 units away from the origin, but we're in the opposite direction. So this would be -3. And that would be a polar coordinate representation for this point. We know that there's many others, but this is one version that actually meets the requirement here for this curve, that we have a theta value of pi over 6. So when you have a theta value equal to a constant, you're really getting a line. Part of that line, you can write down the points with a positive r value. Some of the other points, you can use negative, and then right at the origin, you would use r equals 0. All right. So these are just 2 very common examples of polar curves that we're going to see. R equal to a constant and theta equal to a constant. Let's put all this together now and look at polar regions. So we're going to sketch the region of the plane where the points satisfy these 2 conditions for r and theta, so that the r values are between 0 and 2, and the theta values are between 0 and 3 pi over 4. And so what we want to do is we want to think about really the endpoints here. What happens when r is 0? What happens when r is equal to 2? What happens when theta is equal to 0? What happens when theta is equal to 3 pi over 4? And so in each of those cases, when we look at just the endpoints, we're really looking at examples of those 2 curves we've looked at. So r equals 0 is just the origin. So it's when the r value is equal to 0, we're right at the origin and nowhere else. Well, let's look at this other inequality, or the other side here of this inequality, r equal to 2. What does that look like? Well, we graphed that. It was a circle of radius 2. All right, so there's what this inequality describes. So if it was just this inequality, we would just shade this in, and that would be our region. But we have this other requirement that our theta values have to meet. And so let's look at the endpoints over here. So theta equals 0. What does that equation look like? Well, that's a line through the origin. And that's where theta is equal to 0. So we just identify the theta equals 0, right? And then it's just a line through the origin. Now what about 3 pi over 4? What about where theta is equal to 3 pi over 4? Well, let's find our 3 pi over 4 ray. So we know that pi over 4 happens kind of in the middle here, in between pi over 6 and pi over 3. 2 pi over 4 is the kind of the positive y-axis here. So then 3 pi over 4, if we go one more, it's going to be over here. So 3 pi over 4 is going to be right here. And so this is going to give us another line. And so what we want to do is we want to think about all the points where the r value is in between 0 and 2, and the theta values are in between 0 and 3 pi over 4. And let's maybe clean this up a little bit. And we're going to just look at, let's shade in the region now. So we want to graph all of the points that are in between theta equals 0 and theta equal to 3 pi over 4. So when we think about that, theta equal to 0 is kind of like our starting theta value, and theta equal to 3 pi over 4 is our ending theta value. So we want to we're going around the circle like this. And we want to look at all the points that have a radius of at most 2. So when we shade this in, actually, it's this region right here. So if we think about all the points here, all of the points in this region have a radius value of r value between 0 and 2, and then a theta value of no less than 0 and no greater than 3 pi over 4. So, it helps to identify where to kind of start the theta value and where to end. So that's essentially giving us this wedge here, this polar wedge, and then the r value tells us how far to go out. So another way to maybe think of this instead of graphing these curves, because it does kind of get a little bit hard to read once you have all those curves sketched. Another way to think of this is, let's go through, let's try it again. Let's start with theta equals 0. So this tells us we're going to start looking for our region here, and then we're just going to work our way counterclockwise until we get to the ending theta value. So this is like our starting theta. And over here, this is going to be like our ending theta. All right, so we have theta equals 0, and let's maybe draw those in just to give us some kind of perspective here. So we're going to start on this. We're going to start at this angle. We're going to work our way to our ending angle here. And then the r value tells you how far to go. So if r can be 0, means we could potentially start at the origin. And if r is up to 2, means this at most we can get up to this r equals 2 portion here. And then we're just going to imagine this going around, and then we stop at our theta value, our ending theta value. So we start at our starting one, we go around, and then we end at our ending theta value. And then the region then is just everything in between. So this would be the polar region. So it's everything inside that wedge and on the edges, because we're allowing it to be equal on those edges. If it wasn't, so if we have like an inequality where there is the possibility that it's equal, you would use, you'd use a filled in line generally. And if it was a strict inequality, then you would use a dotted line. So that's the same idea for intervals. When we draw points on a curve, We use a filled in circle to indicate that we want to include that point, and we use an open circle to mean that we want to exclude that from our curve. So, think of that as like the difference between a filled in dot when we're drawing a curve versus an open circle. When we draw our curve. All right, so there's our polar region. Let's try another one of these. All right, so we have another polar region here. We're given an inequality for r, so r is between 2 and 4, it could be equal to 2 and 4. And then we're given inequality for theta. So theta is between pi over 3 and 3 pi over 2. So again, let's start with the theta values. And let's start by figuring out where the starting and where the ending versions are. So we're going to look at the starting, and then we'll look at the ending theta value. So we want to start at pi over 3. So that's right here. This is our pi over 3 ray. And what is 3 pi over 2? Well, 3 pi over 2 is the negative y-axis. So we have our starting ray, pi over 3, and then we have our ending ray, which is 3 pi over 2. And we're going to work our way counterclockwise. So we have our starting ray, and we're going to work our way counterclockwise until we get to that ending ray. So we're starting with pi over 3, working counterclockwise. So let's now look at the r values here. So right on pi over 3, we could have an r value of 2. We could have an r value of 4. And then everything in between those is perfectly fine. So what we can do is imagine this ray that's sticking out of the origin, and then just imagine rotating it around the origin. And this is the section here that this is the section here that's going to kind of trace out our region. So we have this ray that's sticking out of the origin. We're just going to rotate it around, and I probably shouldn't. It's probably going to be mirrored, and we want to go counterclockwise. So we're going to rotate this around counterclockwise. So we're going to go in this direction. And then just keep track of where this section of our line here, this line segment, keep track of what that's going to essentially trace out. And when we do that, we're going counterclockwise. Eventually, when we get down to this 3 pi over 2 ray, we're going to be at these 2 points here. And so when we trace that out, the r equals 4 is going to give us sort of an outer circle. The r equals 2 is going to give us like an inner circle. And then we're tracing out this region that's in between. And so this is kind of a section of, well, let's call it an annular region. So it's part of an annulus. So sometimes you might hear that terminology with polar coordinates. So, an annulus is just kind of like a donut shape. All right, so this is really how to kind of think of these when you're sketching polar regions. You really start with the angle. That tells you, you imagine you have your starting ray, and then you have your ending ray, 3 pi over 2 in this case, And then you look on that starting ray, look at the r values. So we start with r equals 2, r equals 4, and then that gives you a section of this ray, and then you rotate it around and you see what essentially what shape is traced out. So when we rotate this little line segment around the origin, and when we stop at 3 pi over 2, we're getting this kind of piece of a donut here. All right. So this is good practice. So being able to picture these regions, these polar regions, is going to be important, and especially if you're going into Calc 3. So these polar regions you're gonna see these quite a bit in Calc 3 when you're looking at double integrals and even into triple integrals. We're going to be looking at polar coordinates and cylindrical coordinates, which is kind of like the three-dimensional version of polar coordinates almost. And so being able to picture these kind of polar regions here is going to be very helpful for when you're trying to do double and triple integrals using these polar type coordinate systems. All right, so being able to have a picture is helpful. All right, let's try another example. So let's describe the following region using polar coordinates. So we're actually given a region here in terms of x and y. So this is a description for a region that is in terms of Cartesian coordinates. And so what we want to do here is we're given a Cartesian description, and what we really want to do is we want to convert it into polar coordinates. This is something else. If you're going into Calc 3, you're going to have to do. So right now we're told that we want, let's sketch the region first. So let's think about what we have here. We want our x value, so we want to find all the points x comma y where the x value is positive or 0. And then x squared plus y squared is less than or equal to 9. All right, so let's think about x greater than 0 or equal to 0. So that means we're looking at potentially, when x is 0, that gives us the y-axis, and then we're looking at everything on the right side here. Now what about this x squared plus y squared is less than or equal to 9? Well, we know x squared plus y squared, we've seen this before. This is the r value. So that means the r value, that's actually r squared. So x squared plus y squared is actually r squared. So saying that our x squared plus y squared is less than or equal to 9 really means r squared is less than or equal to 9. And we can solve this for r by doing the square root of both sides. So, well, we'll put that off for a second. And let's think about x squared plus y squared equal to 9. Let's think about what happens when x squared plus y squared is equal to 9. This is a circle of radius 3 centered at the origin. So let's draw a circle of radius 3. And so if x squared plus y squared is less than y, or less than 9, means we're inside the circle, but we want only the points that have an x value that's 0 or positive. So we're actually only looking at this section. So x squared plus y squared less than or equal to 9 gives us everything inside the circle of radius 3, but this extra requirement that x is greater than or equal to 0 means we're just getting the right half side of the circle. All right, so now let's convert this into polar coordinates. And we kind of started there by introducing, converting that x squared plus y squared into r squared. And if we solve that, we know polar coordinates can have, multiple representations in terms of different r values. It's going to be most convenient if we try to keep the r value positive here. So we're going to say r is between 0 and 3. All right, now what about the theta values? So now we have our region sketched in. We want to find the theta values that go with this. And we're always thinking in a counterclockwise rotation here around the origin. So here's our origin, and we're always thinking in a counterclockwise. So we want to trace this region out counterclockwise. So that means if we're going to go counterclockwise, this would be our starting ray. So we're going to start over here. And then if we go around and then we end up here, means this is going to be our ending ray. So we need to find the theta value for this ray down here and this ray up here. So what are the theta values? And we want, if this is our starting ray, the theta value for our starting point has to be less than the theta value for our ending point. So we might be tempted to think this is pi over 2 and this is 3 pi over 2. The issue here is that our starting theta value has to be less than our ending theta value. So this is a good ending theta value, pi over 2, but the starting one, if we're going counterclockwise, it's too big. We're already starting with a higher theta value. So instead, technically this is correct, but we know that each ray has many different potential theta values, and we can add and subtract 2 pi as much as we need to. So we just subtract 2 pi until we get it lower. So 3 pi over 2, probably how I would remember it. But it's too big relative to this ending theta value that we've chosen. So let's subtract 2 pi. And subtract as many 2 pi's as you need to until it gets smaller. And in this case, once is enough, and we get negative pi over 2. So our starting ray here, another way to think of this starting ray is with theta equal to negative pi over 2, and then we're going around the circle until we get to pi over 2. So let's write down our description. So we're given our Cartesian description where x is greater than or equal to 0 and x squared plus y squared is less than or equal to 9. We found that r is between 0 and 3. And you can kind of look at this region. If we think of it right at the origin, if we look at the starting ray, the origin here is when r is 0. We go out and we get to this point right here. That's where r is 3. And then we just rotate that around counterclockwise until we get to this ending ray. So the r value is between 0 and 3. And then the theta values are going to be from negative pi over 2 to positive pi over 2. Now there's potentially you could add 2 pi to all of this, and it would to both sides here, that's another way to go about it. So we could have started with the 3 pi over 2 and said that was good, and then gone to 5 pi over 2. Perfectly fine. Sometimes it's easier just to kind of keep things within the as the theta values as small as possible, or as close to 0 as possible, rather than having them get larger and larger multiples of 2 pi in there. So this is fairly standard. If we have to go negative, normally that's okay. So this would be kind of a good representation for this. But another version would be, say, 3 pi over 2 to 5 pi over 2. Also perfectly fine. All right, so there's our polar representation. So we were given our region described in Cartesian coordinates. We converted into a polar coordinate representation. And there's the region. All right. Let's try another example. And this is just going to be, we're given a polar, or we're given a Cartesian equation, and we just want to convert it into a polar equation. All right, so we want to find a polar equation for the line given in Cartesian coordinates by x equal to 4. So this is just a vertical line at x equals 4. All right, so how we do these, we want to convert from Cartesian. So really what we want to do is we want to go from Cartesian into polar. So we want to think about what are the general equations that we have to work with when going from Cartesian into what are the general things we have to work with. So we have the x equal to r cosine theta. We have y is equal to r sine theta. And then if need be, we could also think of r squared is equal to x squared plus y squared. And then tangent theta is equal to y over x. So these are all little equations that we can use to help us convert over a Cartesian equation into polar coordinates, or the other way around. So let's look at this x equals 4. And we know what x is. X is r cosine. So we can actually plug that in. Wherever we see an x, change it to an r times cosine. If we saw y's, we could change a y into r times sine theta. So let's start with our Cartesian version here, x equal to 4. And we're just going to change that x into r cosine. So we know r cosine theta is equal to 4. And when we write down a polar equation, a lot of times we want to solve for r. So we're going to see more examples kind of like this next time, where we have r is equal to. So let's solve this for r. Not absolutely necessary here, but usually helpful. So we're going to solve for r. And that means we're going to divide both sides by cosine. So we're going to get r is equal to 4 over cosine. And then what's the reciprocal of cosine? Well, we can simplify this down. So 1 over cosine is secant. So this would be 4 times secant theta. So we get r is equal to 4 times secant theta. So we have our Cartesian version of this vertical line that happens at x equals 4. Here's our Cartesian equation. And we've converted it into this polar equation. And these are going to be the forms that we most readily see. R is equal to, and then a function of theta on the right-hand side. Polar. Yeah, that's an equation, but it's a polar equation. All right. What was the next one? we'll try this one next time. So I think that's a good breaking point. So we'll see next time. So in this one, we saw how to go from Cartesian coordinates into polar coordinates. Next time, we'll see we're given a polar curve. We'll see how to convert this from polar equations into Cartesian equations. And then we're going to see how to actually graph polar curves like this. So we looked at a few easy polar curves, r equal to a constant, theta equal to a constant. We're actually going to see how to graph more complicated ones like this next time. All right. So we'll see you then. Bye-bye.